Hello, welcome to the Food Network. This is Cooking with the Actinites. Today we're going to be making popsicles, and Marley's going to show you about the ingredients.
To make popsicles, you need 2 freshly squeezed oranges, 600 milliliters of juice, 3/4 cup of sugar, 2 cups of boiling water, and some popsicle makers.
And now we're going to come over here and put the sugar into this boiling water to kind of dissolve it. And then we're going to get a little stir thing out. I'm going to stir that around. Making popsicles or cooking in general, you have to start to think what kind of pan or utensil to use. And believe it or not, chemistry does play a role. Inside of cooking and chemistry is this concept called specific heat. Specific heat is the amount of energy needed to raise a substance temperature up 1 degree Celsius. In our case, we are using a steel saucepan with a specific heat of about 0.46. This steel pan is more efficient than an aluminum pan because it has a lower specific heat, but also less efficient than a copper pan because it has a higher specific heat. In the case of steel, a 0.46 specific heat means that to raise a degree of Celsius of the pan by 1, I need to put in 0.46 joules of energy. In the case of all pots and pans, it is most efficient to use a material with the lowest specific heat, for that means less energy needed to get the temperature needed. Finally, specific heat is just as important in the cooling process as it is in the heating. The same way it takes 0.46 joules of energy to heat up our saucepan, it will also take 0.46 joules of energy to cool down our saucepan. Our solution is mostly water, and water has a specific heat of 4.18. This is considerably important, for it dictates how long our popsicle mixture will take to freeze. And since water's specific heat is so high, it will take longer. Specific heat is an active concept in cooking and something to definitely be aware of.
Now pour the sugar solution into a bowl to make the popsicle solution.
And now we're going to add the juices.
To make popsicles, we look at 3 main ingredients: water, sugar, and citric acid. All of the ingredients have at least 1 hydrogen atom, so they have hydrogen bonding as their intermolecular force. Intermolecular forces are the attractions between molecules or ions. We are going to look at water as our example. Water has 1 partially negative oxygen atom and 2 partially positive hydrogen atoms, so they are bonded together because of the charges. Even though they are bonded together because of the charges, the force is not super strong, so it does not take a lot of heat energy to break it apart. This is what the molecules look like before the water boils. This is what the molecules look like after the water boils. When water boils, the intermolecular forces disappear. As the water gets hotter, the molecules are moving around faster and faster, and it slowly turns from a liquid to a gas.
And mix those around as well, just so that...
So heat energy can be transferred by 3 different ways: by radiation, conduction, or convection. And as we heated the pan, as shown up there, dissolving the sugar, the heat of the stove was transferred to the pan by direct contact, which is known as conduction. They were touching each other, meaning the stove and the pan, and so the stove transferred its kinetic energy to the pan. As the sugar was gaining energy, we began to feel the heat from the pan and the sugar. This is another type of heat transfer known as radiation. The heat from cooking the sugar was radiating from the pan, which you were able to feel without touching it. This is because currents of air were heated and warmer molecules were rising and were becoming less dense, while the cooler molecules sunk to take their place. That is known as convection. It is the transfer of heat energy by the motion of liquid.
We started our cooking video earlier. We saw that we started with super hot water, not quite boiling yet, so I'd imagine it started right about here, right around the 90 degrees Celsius range. We put it on a burner, and it heated up to 100 degrees Celsius, and at that point, it began its phase change. And during the phase change, please do remember that temperatures do stay extremely constant, and we use the equation Q equals mHV. Q equals the mass of our water times the heat of vaporization. Now, once we see steam rising and it starts to evaporate, that is a signal that the phase change has occurred. and we then took it off the burner. Once we mixed our popsicle solution, built it all together, we actually threw our popsicle back into a freezer. So we started right around, I'd say, 90 degrees Celsius again. That was pretty hot. And once we put it's in the freezer, it's cooling down to 0 degrees Celsius. And once it reaches 0 degrees Celsius, it's actually going to begin freezing. And it should take about 15-20 minutes at that point, and then we'll get it to a solid. If we look at, as Jack Burney stated earlier, there's something called specific heat capacity. And you use the heating curve to calculate that with all these different equations I've written.
Voila! Popsicles!